Imagine yourself on the SpaceX Crew Dragon about to launch. There's a huge clock tower at the launch pad. You see the seconds ticking by. 3, 2, 1, blast off! Now let's pretend you're traveling at the speed of light. You look back and notice the clock tower doesn't appear to be moving. You know that back at the launch pad, time is ticking away as normal, but because of your tremendous speed, time appears to slow down. Wait, is that even possible? Turns out it is! You are experiencing something called time dilation. The basic idea of this is, the faster you move through space, the slower you move through time. So you're probably wondering, wait, how does this actually work? Well, let's take a look. Here I have a light clock. It consists of 2 mirrors and a beam of light. Each time the light hits a mirror, a second passes. So let's say you had one of these with you at the launch pad. Your friend watching from the field also has one. When you start to move, your friend observes that the beam of light of your clock travels diagonally. Since the beam of light now has to travel a greater distance, each second takes longer than your stationary friend's clock. Essentially, your time has slowed down because you are moving. So you might be wondering, how much does time say dilate when moving? Well, let's start by looking at the equation for time dilation.
Whoa, this looks complicated. Let's just start by defining the variables. T prime equals time of stationary observer. T equals time of moving observer. V equals velocity of moving observer. C equals speed of light. Alright, that's a little better, but what does this really mean? Let's break it down some more. To start, we know that there's definitely some kind of dilation going on because time for a stationary observer doesn't equal time for a moving observer. Next, the speed of light is huge, approximately 186,000 miles per second. The velocity of a moving clock will always be minuscule compared to c. For reference, the Crew Dragon we used in an example at the beginning had an escape velocity of 7 miles per second. Not even close. So v squared over c squared equals small over huge, which is pretty much 0. So 1 minus pretty much 0 is pretty much 1. Zoom out a little more and the square root of pretty much 1 is 1, pretty much. Phew, almost done. T over pretty much 1 is pretty much t. Finally, we see that t prime is pretty much t, meaning the time experienced by a stationary person is pretty much the time experienced by a moving person.
Basically, the effect of relativistic time dilation is so small in our everyday lives, we don't notice it. This type of time dilation is only really relevant and noticeable when traveling near the speed of light. So you're probably thinking, why bother learning about this if I won't ever notice it? Well, I think understanding time dilation is motivation to create better, to get to the next level of discoveries. The Crew Dragon traveled at about 0.003% the speed of light. Imagine how much more could be accomplished if we could travel fast enough to experience the benefits of time dilation.